Thanks so much. Thanks, Alex and David, for the introduction. It's really great to be here, for the invitation to speak. I've got a couple conflicts to declare. So I'm preaching to the choir that B0 is a, oops, we've got Zoom on our slides. Sorry. So I'm preaching to the choir that B0 is a big problem at 7T because we're really interested in measuring the microscopic T2 star weighting, for example, in bold fMRI, but we're confounded by the overlaying T2 star created by tissue susceptibility interfaces in the body. Of course, we buy a beautiful magnet from Siemens, but then as soon as we put a messy human body into it, we mess up that homogeneity. And that's going to cause not only difficulties measuring the microscopic T2 star that gets worse at ultra high field, but it creates a variety of image artifacts. For example, signal voids in gradient echo imaging, geometric distortion in single shot EPI that gets worse at ultra high field.
Sorry, it's not following the slides, people's.
Oh, to the Zoom. And a lot of these artifacts are difficult to correct in post-processing, or in the case of signal voids, they can't be corrected in post-processing. So another example is banding in SSFP. And then a less commonly cited one that I think is interesting is distortion of the slice profile, shown by Anna Blazejewska. You also get chemical shift issues in line broadening in MRSI. And B0 makes PTX much harder because you have to design your PTX pulses to be robust to delta B0. And I like to make the point that this really underscores why B0 and B1 need to be addressed together at ultra high field. And you always need to think about the interaction between the two. So how do we deal with B0? The most common method is with shimming. So you go to IKEA, you buy a dresser and you put it together. Well, in Boston, in all these creaky old houses, the floors look like this. So you have to shim it to make it flat again. And you do that with a mechanical shim. Well, you also can shim magnetic fields. If you have a B0 challenge, you can create a compensating magnetic field that restores homogeneity. And that's framed as a problem using whatever degrees of freedom you have, a target field in vivo B0 map, and a quadratic program to build the best compensating field that you can. So we do this with first and second order fields on most scanners, sometimes a few third order fields as well, generated either by the linear gradients or by higher order shim coils that look like this. But most of the heavy lifting is done by those first couple spherical harmonic terms. So you get most of your benefit just from the first and second orders, and you get diminishing returns at higher orders. So if you wanted to go for up to 19th order, you'd need 400 spherical harmonic shim coils, which is not really practical. And then even then, you can't get a perfect shim because the sources of tissue susceptibility inside the head violate Laplace's equation, for which the spherical harmonics are an orthonormal basis. So to get a perfect shim, you have to put sources really inside the head. Okay, so that's frustrating. Can we do better? In 2D imaging, we can by updating the shim on a slice-by-slice basis. And this really improves the homogeneity because you're reducing the volume that you're shimming at any given time. All right, so we want to build a shim coil. Where do we put our shims? And how do we fit them into a crowded bore? So here's just a picture of my house in Boston. No, just kidding. This is the most expensive house I could find for sale at the moment, but it's still cheap compared to the space inside our Terra X, about 6,000 times cheaper per cubic meter. So how do you fit shim coils into this small space, even smaller when you have an impulse gradient, without having problematic coupling to the gradients, to the RF transmit, the RF receive? So there's three basic ways to handle this precious real estate. The first is you can do a spherical harmonic shim insert where you hand pick a couple higher order shim terms that give you the best bang for your buck. And this has been done by resonance research. And they've even shown you can dynamically update these shims and pre-emphasize them to deal with eddy currents. And they get some pretty nice improvements in global shimming, as shown here at 7T. But can you do other things? You can. You don't have to use an orthonormal basis. You can actually just create a generic array of loops called a multicoil, driven with low currents that have relatively modest inductance. You can switch them quickly with minimal eddy currents, lower coupling to the gradients. And if you put them outside your transmit shield, they don't mess up your RF transmit and receive. So Christoph Yukum introduced this originally, and it's been beautifully adopted by Klaus Scheffler at 9.4T as shown here, giving really nice improvement in homogeneity. There are some issues. You get acoustic noise, torques, and you can get voltage induced by scanner gradients. So are there other approaches? Well, at MGH and also at Duke, we've looked at using the actual RF receive array as a source of shim fields. You do this by adding DC capability to your receive loops, and then you can rapidly switch them with low voltage amplifiers. And it's kind of synergistic because both types of arrays want to be close to the head and want to have many channels to boost parallel imaging performance, RF sensitivity. So they want the same thing, basically. So I'm happy to say that we've now actually implemented this on GE as well as Siemens, and it's working on Cowan and Adams UHP scanner at Stanford. And as a step toward more widespread adoption of these tools, we were able to sort of integrate the shim plugs and amplifiers really into the scanner, so it's a better user experience. And we've seen that we get some improvements with dynamic shimming. The standard deviation goes down from 32 to 17, and especially in the superior half of the brain, you see more appreciable improvements in distortion. So that's 3T. Will it work at 7T? 7T is a lot scarier. So in honor of Friday the 13th, we built a scary mask for our 7T shim coil. And we used that to build our 32-channel receive array, and we also added some shim coils over the face, which you can see here. And those are targeting the frontal lobes especially. So that's the reason for this sort of scary hockey mask. And we were pleased to see that adding the shim hardware really didn't impact the sensitivity or the G factor. And we've now been using this to reduce geometric distortion in single-shot EPI, as you can see here in these slices. Not perfect, but it's an improvement. The limitations of this approach are that you only have a single turn to carry your shim currents, so you may hit the current limit of the amplifiers, and you still have to be careful running all these shim wires inside your transmit array that you don't couple to the transmit coil. So it still has its challenges. Now, I've shown how increasing channel count can benefit shim performance. How can we get good shim performance using the minimum number of channels possible? Simplify the shim array and simplify the wiring and amplifier requirements. Well, you can try to design your shim coils specifically for the human anatomy instead of using spherical harmonics or a generic multi-coil. And this is really inspired by how we build gradient coils. You use a stream function approach with a prescribed geometry to solve for the optimal current density on that surface, and then you turn it into isocontours of a wire pattern. Then you can do this separately for different subjects in a B0 map database. And then using an approach like the SVD, you try to compress it down to one or a few modes that span the whole population of human heads. So for the aforementioned shim coil that we're designing for Berkeley, I'm looking at this approach with Théodore Frière, a visiting student, and he's looking at using one or more layers of current to try to get robustness across the whole population of humans. And so he's looked at 1 and 2 channel approaches. He's also looked at segmenting each layer into sectors, which is denoted by S here. So here's like a 9-channel and a 10-channel approach, mixing layers and sectors. And he's simulated performance against benchmark coils like an AC/DC coil or a generic multi-coil, such as that shown here. And he sees a pretty nice improvement in performance, even using only the 2-layer, 2-channel approach in global shimming. You do get better performance with your multi-coils, but that comes at the cost of increased hardware complexity. I'm not mentioning here that the multi-coils are better for dynamic shimming because you can separately tailor the field for every slice. But if you're doing 3D imaging, you have to do global shimming anyway. So the global shimming is still very important. Now, one thing that's on our minds, especially for the impulse gradient, is coupling between the scanner gradients and the shim coils. If you have a lot of voltage induced in the shim coils, you need a lot of voltage compliance in your shim amplifiers, disturbance rejection. And I think we may hear later today about how there's already issues on the Terra X of coupling between the third order shims and the scanner gradient. So we want to look at mutual inductance between the impulse wire pattern in our shim coils. Well, for the stream function coils, you can see the worst case voltages are maybe around 11 volts, which is still manageable. For the AC/DC, the voltages are very small because they're just single turn loops. And for the multi-coil, it depends how many wire turns you use. So there's really a trade-off. As you add more wire turns, you get better performance, but you also have more power dissipation and more coupling to the scanner gradients. And we can't compensate for a 60-volt EMF using our shim amplifiers. So there's some engineering trade-offs that we're thinking about, and we don't have our optimal solution yet, but we're working on it. I think 20 turns might be the Goldilocks. And this is going to be built into one of Shaojian Gunamani's forthcoming RF PTX coils, and it's going to be built into a detachable housing shown here as an orange cylinder. And this is outside the RF shield, so it shouldn't interact with the RF system. And we're working on a 48-channel open source shim amplifier that will operate inside the magnet room. I was staying in Palo Alto, and I saw the Packard garage where Silicon Valley is rumored to have started, so-called birthplace of Silicon Valley. And I guess Hewlett and Packard were working on an audio amplifier in here. And I was like, oh, Gang Chen and I were working on audio amplifiers in his garage on Sunday. So I've had my first Silicon Valley garage electronics experience. So, also doing an audio frequency shim amp. So I've talked about B0 shimming. Now, in the time that remains, I want to ask the question, what else can we do with nonlinear, rapidly switchable B0 fields inside the scanner? And I just present a few topics as teasers, but what I'm really interested in is hearing people's ideas for this stuff. The body anatomy is curvilinear, right? Find me a right angle anywhere in the body. So why do we use linear gradients for everything? Can we actually use switched nonlinear gradients? So with an AC/DC coil, of course, we're trying to get as much out of it as we can. We do Faraday detection, the NMR signal, we do parallel imaging, and then we do artifact reduction and anatomic imaging, like distortion correction. We've shown that you can clean up line widths in MR spectroscopy. That's all conventional stuff. But we've also tried to play around with different kinds of switched fields during a sequence. So if you switch on your shims just during lipid suppression, can you tailor the field so that you improve the lipid suppression pulse and then switch back to a homogeneity shim for excitation and readout? We're also playing around with different types of shim waveforms during RF excitation. So can you use these with linear gradients to improve the performance of PTX pulses? And something I looked at with John is to actually do zoomed selective excitation using the shims, as shown here. Danny, I see you're in the audience. We're looking at whether you can do flow territory mapping by shaping the nonlinear field to select just one of the carotid or vertebral arteries in the neck for ASL. And then we're thinking about spatial encoding, so either to build linear or nonlinear fields using your degrees of freedom. And then the latest thing we've started to play with is eddy current and concomitant field correction. So I only have time to touch on these last two, which I'll briefly highlight for you. So to do dynamic waveforms during the pulse sequence, we needed to build new amplifiers. Won't go into the details, but if you're interested, I'm happy to chat about it. This is an FPGA system that controls up to 64 shim amplifiers at 4 amperes per channel, and it operates inside the scanner room. And we can now play out, arbitrary waveforms up to about 10 kilohertz. And here's just an example of a sine wave. It gets 1 kilohertz that we measured with the scope camera, and we verified that the field tracked the integral of the current through one of our AC/DC loops, so that's good. So one of the applications of this that we're working on with Chongyu and Cowan is 3D diffusion prep BISP, where you actually are doing distortion-free readouts with a prep and then a spoiler. And the problem is that these diffusion gradients have some eddy currents that can lead to residual phase before the tip-up pulse. And that requires a spoiler, which can cost you a factor of 2 in SNR. So our question was whether we could blip the shim on and off before the tip-up pulse, here shown in green. We turn the shim on and off by triggering it with the red arrows, and we generate a field that matches the eddy current-induced nonlinear phase profile. And Chongyu showed that this actually does clean up some artifacts in his 3D diffusion API, which was really gratifying to see. So another thing we're looking at is spatial encoding with these multi-coils. And this can be done using really beefy multi-coils, as shown by Christoph Yukum's group, to actually synthesize and replace the linear gradients. So in this case, they're not using linear gradients. But you can also use it as a supplement to the linear gradients by playing out either a sine wave or some other modulation during readout. And Klaus Scheffler has shown that this allows parallel imaging using just multiple B0 coils with one RF receive channel. So you're shifting from RF receive encoding to this oscillating gradient encoding. And Cowan and I played with this idea using much smaller perturbations of B0 with an AC/DC coil using a wave trajectory that then has a little fuzz added to it, shown in the bottom right, using the sine wave on the AC/DC. And this can improve the conditioning of the recon by improving voxel spreading. Just a warning, this may be loud depending on how the sound is. Again, loud problems. But if you can hear that little bit of sound, that's mostly our AC/DC coil. And so it does actually clean up the artifacts in these wave images a little bit. And so in this case, we're making the AC/DC coil work hard. It's doing our signal detection, our parallel imaging, and some extra spatial encoding at the same time. And I also, just as a toy example, tried switching off the scanner gradients completely in a gradient echo acquisition, and we created a multi-coil synthesized linear gradient, and we were able to do some very simple gradient echo imaging with a beefy gradient strength of 0.25 millitesla per meter. So, but it showed the principle. And the last thing I wanted to show in just the last few minutes is how we can use our new shim amplifiers for eddy current compensation. So this is, I think, an issue we're going to hear about a couple times today, the fuzzy ripples that Renzo identified, which come from small imperfections in the gradient waveform, either caused by imperfect eddy current compensation, GPA regulation issues, vibrations, complicated combination of factors. And the idea is to switch the shim array so that it fills in that missing gradient moment. And since this is a relatively small field we need to generate, one of our shim coils might be able to handle it. So we characterized the gradient waveform with a scope camera and then used our degrees of freedom along with a constrained optimization to fit each shim channel to play out a waveform that will emulate the missing field. And so turned out the target field was actually nonlinear, but if you look at the linear component of it as measured by the scope camera, the orange curve is the baseline and the blue curve is with the AC/DC applied. So we saw some improvement in the field evolution when we apply our correction. And our next step is to hopefully see that this helps with the artifacts themselves. So I think not to steal Cowan's thunder, but he's going to show that you may be able to address this in software. So we may not need these coils, but I close with this sort of question. Have I shown you a Swiss Army knife that does lots of useful stuff or a hammer that's looking for the nail? And I think the question is how to synergistically combine hardware and software. For example, retrospective corrections may help a lot, but if you improve the B0 to start with, you may improve like the distortion correction you get with top up. It will help your algorithms to work better if you improve the conditioning of the recon. And there are still cases where, disrupted RF pulses, gradient echo signal voids where you need better shims, steady state magnetization. But I think sharing the burden between hardware and software in a synergistic way is where I see opportunity in the future. And then there's also this question of nonlinear gradients that can do things the linear gradients can't do so easily, because either you can tailor the nonlinear field to the human anatomy, or because you can operate these local shims at very high temporal frequencies you can't do with the scanner gradients. So that's all I had, and just a shameless plug that we're looking for a hardware-oriented postdoc. Thanks so much.